Good evening, students. This is just a repetition of video lecture L.10.5, in which we learn the quantization of complex fields, and thereby we quantize the energy of the photon. And we discuss the eigenvalue of the energy of the photon using modified Klein-Gordon relativistic equation, which is for bosons. Of course, photon is a boson, and that's why we use Klein-Gordon equation, which is for bosons. There are three terms in this expression, and I gave one term as an assignment. And it seems that students find difficulty in solving the second term. In this video, I am going to derive all the three terms and get the expression for the quantized energy of the photon. In this lecture, we are going to use complex fields. We are going to follow the same procedure as we have done for real scalar fields. Scalar field means a single entity which will have real values and complex values. Real value implies a photon creating a particle and antiparticle, whereas complex fields involve more than two particles, more than two systems. If we have number of particles and antiparticles, we do not know what combination of these two particles would be. Then we will have to think of only complex scalar fields, which will have more than two particles and more than two antiparticles. In Klein-Gordon wave equation, we use the field functions, namely field operators phi and momentum density pi. Both depend on x and t. They are written in terms of creation and annihilation operators with the plane wave equation. So with this introduction, let us start the quantization of complex scalar fields, by which we are going to get the quantized energy of the photon. If the field functions phi of a scalar field are complex, then we have a complex scalar field which describes a charged particle in the quantized theory. The quantization of complex field is derived similar to the real scalar field. It was first carried out by Pauli and Weisshoff. We know that a complex field is described by the field variable phi by splitting into real and imaginary part as phi equals phi1 plus I phi2 divided by root 2, and the complex conjugate of phi, the field operator, which is nothing but phi star, which is equal to phi1 minus I phi2 divided by root 2. Here phi1, phi2 are real values, whereas I phi2 is there. So this is your real part and this is your imaginary part. And of course, we are going to use the Hamiltonian, which is given by this slide. And this is modified Klein-Gordon relativistic equation. And of course, we are going to have the expression for your phi and pi. Your phi is nothing but field function and your pi is nothing but momentum density. And this is your first term, and this will be your second term, and this will be your third term. And but they are not Hermitian operators. Look at phi and phi star. Actually, operators will be denoted by phi dagger. Usually, operators will be denoted by phi dagger. So something like this. You see, you have phi1 plus I phi2 divided by root 2 and phi dagger. Usually, generally in quantum mechanics, all the operators will be denoted as dagger. So that's why instead of star, we have written as phi dagger. So phi dagger, which is equal to phi1 minus I phi2 divided by root 2. And it implies that phi is not equal to phi dagger. See here. So they are not Hermitian. They are not Hermitian. Okay. Now we'll have the expressions for your field operators, field functions. The phi1 is given as 1 by root p sigma over k 1 by root 2 omega k ak1 e power ikx plus ak1 dagger e power minus ikx. And as I said earlier, the field function depends on creation and annihilation operator and the phase factor. Similarly, so phi1 stands for particle 1 and phi2 stands for particle 2. And the field function for particle 2 is given as equation 10.10, 10.90. And we are going to use equation 10.88. So 10.88 is given as this one. And phi of x is given as, where phi x is equal to 1 by root p summation over k 1 by root of 2 omega k ak1 plus iak2 divided by root 2. So we are going to add, see, this is where 10.88. We are going to add the first term ak1 plus iak2 divided by root 2. See here, we are going to add these two, 10.81 plus 10.90, real term with real term, imaginary term with imaginary term, and use this equation, phi equals phi1 plus I phi2 divided by root 2, which is equation 10.88. So use this equation, we will get equation 10.91. So ak1 plus iak2 divided by root 2 e power ikx. So use this equation. Similarly, adding this term, you will have this term. So now your phi dagger is given by equation 10.92. You just take the complex conjugate of this, you will get this. So your phi of x is given by this equation 10.91. Take the complex conjugate, you will have 10.92. See here, it is plus ia, here it is minus ia. E power ikx, e power minus ikx. And similarly, this term also, just take the complex conjugate, you will have this term. So equation 10.92. So this is your phi dagger. Now, we are going to simplify these two equations as 10.93 using this term, that is ak plus or minus, which is equal to ak1 plus or minus iak2 divided by root 2. See, now what we are going to do is, instead of this term, we are going to use ak plus, and this term can be replaced by, here this is replaced by, you are going to take the complex conjugate. When you are going to take the complex conjugate, see, this is iak2 dagger. So this will become minus. So real part, of course, if you take the real complex conjugate real part, the real part itself. So you have ak1 itself, but this term will become minus. So you have ak1 minus iak2 dagger. So this term can be replaced by ak minus, and this term can be replaced by ak plus. See here, look at the equation 10.93. So this becomes ak plus e power ikx, and this term becomes ak minus dagger e power minus ikx. Similarly, this term also can be written. See, this term can be written as ak minus, whereas this term you are going to take the complex conjugate. So this term will become plus. So ak1 dagger plus iak2 dagger. So this term will become plus, as I said. So minus becomes plus. So ak1 plus iak2 dagger. So this will become ak plus, and this will become ak minus. Look at this equation. See here, as I said, ak minus, and this will become ak plus. So this is equation 10.94. So you have now phi dagger. So we have now phi and phi dagger in this equation. Now we are going to use the commutation rules. The commutation rules are given as equation 10.95. The commutation rule for your field operators are given as 10.96. And this is your commutation relation. So that is AKI, commutation bracket with AKI, AKJ dagger, which is equal to IH cross del KK dagger, and del IJ is given as when I, j equals 1, 2. And you have the self The complex conjugate, the self commutation rule is aki, akj, which is equal to aki dagger, akj dagger, which is equal to 0. So we are going to use fully this quantization rule. So what we call this quantization rule, commutation rules. And of course, as I said earlier, and this is the commutation rule for field operators. So we are going to use 10.95 and 10.96 to simplify the problem, to simplify the derivation. The operators which are in the field functions and in momentum density, ak dagger and ak plus dagger are interpreted as destruction and creation operators for a positively charged field. So this is A plus is there. So this is for a positively charged field. And similarly, AK minus and AK minus dagger are interpreted as destruction and creation operators for the negatively charged field. So if minus is there, this is for negatively charged field. If plus is there, and that is for the positively charged field. Now, similarly, the annihilation and creation of momentum densities correspond to real fields phi 1 and phi 2 are given by phi of x is given by equation 10.97 and phi dagger of x is given as equation 10.98. And of course, we are going to use modified Klein-Gordon relativistic equation, which is as 10.99. So we have taken only from this equation. See, we have taken already, we studied earlier in the previous video lectures, we studied this equation. Your phi squared becomes phi dagger phi. Your del phi squared becomes del phi dagger del phi. And m squared, of course, you have as it is. Your this phi squared last term, phi squared becomes phi dagger phi. So now we are going to use the first term. So this is your first term, and this will be your second term, and this will be your third term. So we are going to derive all the terms in this video lecture. We are going to derive. This is your field functions. This is your field operators. Derivative. This is your field operator, and this will be your grad derivative, derivative of field operator, and this is your momentum density. So now we'll first take the first term. So equation 10.99, we are going to solve, we are going to simplify the first term. The first term goes like this: integration over t cube x pi dagger pi, which is given as equation 10.100. See here, we have pi dagger equation. See, we have the expression for pi dagger. We have the expression for pi 2. You just substitute here. So this is the expression for your pi dagger. This is the expression for your pi. The first thing that we are going to simplify as you multiply I with I. First thing. So I with I, that will give you I squared, which is equal to minus 1. And second one will be 1 by root v multiplied by 1 by root v will give you 1 by v. Then root of omega by 2 under root multiplied by root of omega k divided by root will give you. So when you are going to k, this will become k prime. So wherever you find dagger, you just substitute instead of k, you substitute k prime. So this will become root of omega k prime multiplied by omega k. 1 by root 2 multiplied by 1 by root 2 will give you 2. So that will give you complete expression will be minus 1 by 2v summation over k comma k prime root of omega k prime integration d cube x, and we are going to multiply this term with this term. When you are going to multiply this term with term, the first term will be multiplied by the first term, the first term will be multiplied by the second term, and second term in the first expression will be multiplied by the first term, and the second term will be multiplied by the second term. See, I have done exactly like this. So we can simplify exactly like this. And we are going to use Kronecker delta rule, Kronecker delta function here. Which says 1 by v integration over volume integral e power I k plus or minus k prime x, which is equal to 1 by v volume integral e power minus I k plus or minus k prime x, which is equal to delta of x plus or minus k prime if k equals plus or minus k prime and omega equals omega k prime. And we are going to simplify equation 10.101 using delta function exactly like this. So look at this equation. First we'll take first term. We have 1 by v, see here 1 by v, d tau e power I plus or minus k plus k prime x equal to delta. So instead of this, we can write delta function. Now, in the exponential term, e power minus I, k prime plus k. So here, this term can be replaced by delta. Here it is k equals minus k, correct? Or otherwise we can say k equals minus k, or other k prime, or otherwise you can say k prime equals minus k. See, I repeat, k equals minus k prime, or you can say k prime equals minus k. So we can write this as delta minus k prime comma k. So this first term becomes, instead of wherever you find k prime, you have to substitute minus k. See here, k equals minus k prime. So wherever you find the k prime, you just substitute minus k. So in this first term alone, so first term becomes a minus k minus dagger ak plus dagger delta of minus k prime comma k. When you go for the second term, so second term clearly says that k prime equals k. So wherever you find k prime, you substitute k. That's all. So second term becomes exactly like this. And third term, wherever you find k prime, that's also replaced by k. So k prime, which is equal to k. So the third term goes like this. And the fourth term, wherever you find k, you'll have to replace the minus k prime. So k prime plus k, which is equal to 0. You can say that k prime, which is equal to minus k. Or so we can, the k prime will be replaced with minus k. See, k prime is replaced with minus k. Now, this equation 10.102 still can be simplified as equation 10.103. See here, what we can do is the first term. You just look at the first term. Look at the first term. This becomes, see, wherever you find, see, this is minus k prime. Wherever you find k, so this is minus k. See, this becomes 1. This becomes 1. This also becomes 1. This also becomes 1. So we have now multiplying with the minus sign, that will give you minus a minus k minus dagger ak plus dagger. See, you just multiply with the minus sign. You will get equation 10.1022 to 10.103. This can be simplified as equation 10.103. And of course, omega k equals omega k prime. So that will give you omega k divided by 2, sigma over k. So we have finished now the expression for your first term as equation 10.99. See here, we have finished the first expression for first term. Now we'll go for the second term. The second term is like this. So you have equation 10.98. We have finished the discussion for the first term. We'll go for the second term now. And second term goes with grad phi and grad phi dagger. So your phi of x is given as this. Already we have seen earlier. And your phi dagger of x is given by this expression. You just take differentiation of the first with respect to x. So you have del phi of x is equal to 1 by root p summation over k, and you are going to differentiate with respect to k. That will give you, so e power ikx, we are going to differentiate, that will give you ik. So I have pulled ik out. Here it is minus ik, so that's why I written as minus I. So del phi is over now. I will go for del phi dagger of x. Already we know the expression for your phi dagger. So we'll have to differentiate this with respect to x. That will give you equation 10.105. See here, you have ak minus, I have pulled ik out again. So that will become this term, 10.105. So now we know the expression for your del phi dagger and del phi. You substitute here. See, we are going to substitute and we are going to simplify. Let us look at the substitution here. We have del phi dagger and del phi. So this is the expression for your del phi dagger, and this is the expression for your del phi. See here, and as I said earlier, for all dagger, we are going to write k as k prime. See, k is replaced by k prime. So this is for del phi dagger and this is for del phi. Now, we'll have to multiply the first term with this first term with the second term. Again, we'll have to multiply the second term with the first term and second term with the second term. We are going to multiply. So now this first term with the first term becomes k prime ak prime minus e power I k prime x. Then multiply with the e power I k x, that will give you e power I k prime plus kx. Remaining thing as I have written exactly like this. So you have k prime kak minus kak prime minus k ak plus. And similarly, the first term with the second term will give us the second term. Then the second term with the first term will give us the third term here. And the last two terms, multiplication of last two terms will give us the last term here. So minus into minus plus. Okay. So simplified one. Now I have written the same equation here. As we discussed, we will have to use Kronecker delta function and your k prime which is equal to minus k. So wherever you find k prime, you substitute minus k. So here the first expression becomes, minus k. Wherever you find k prime, so your minus k. Of course, the integration will go off. Using Kronecker delta function, the integration will go off. So we have instead of k prime, you substitute minus k. Instead of k prime, you substitute minus k. So the remaining let it be like this. And go for the second one. In the second term, k equals plus k prime. See here, k prime equals plus k. So as it is. Now there will be no change. Only thing is k prime is replaced by k. And what about the third term? Third term again k is replaced by k prime itself. So wherever you find the k prime, you substitute k. That's all. And fourth term is k equals minus k prime. So wherever you find k prime, you have to replace it minus k. So again this term becomes minus n here. Already one minus sign is out. Here one minus sign. Just multiply with the minus sign. So equation 10.107. See here. So you will get, you pull k out. So that will give you k square divided by 2 omega k. I have multiplied with the minus sign. So all terms will become plus. So that's the second term of equation 10.99 becomes. So this is what I gave as an assignment. So I have done for you. So this is equation 10.107. Now the last term. We'll go for the last term. Last term is m squared pi dagger pi. So we know already pi of x is given by this expression. Pi dagger of x is given by this expression. And we are going to simplify integration over d cube x pi dagger multiplied by pi. See here. Now this is your pi dagger and this is your pi. So we have taken all these common terms out. So this is given by this expression. And you're going to multiply the first term with the first term. When you're going to multiply with the first term you will have ak dagger minus ak plus e power I k prime plus k dot x. Similarly, second term, first term with the second term, we have obtained the second term here. And similarly, second term with the first term, third term here, second term with the second term will act as a fourth term here. As usual, the same argument. For the first term, k prime equals minus k. So wherever you find k prime, that should be replaced by minus k. Here it is plus k. So k prime is replaced by k. Here also it is k prime is replaced by k itself. But here is k prime is replaced with minus k. So I have simplified exactly like this. Okay, I have pulled the common terms out. So we have done exactly like this. So last term. So this is our last term, which is nothing but d cube x integral d cube x pi dagger pi is given by this expression 10.109. So now we have derived all the three terms in equation 10.99, which is nothing but modified Klein-Gordon relativistic equation. Now we are going to substitute. And this is the expression for pi dagger pi, so which I have written here for the first term. And this is where the expression for second term del phi dagger del phi is given by this expression, and phi dagger phi is given by this expression, and of course m squared is here. So now 10.110 is exactly seen as exactly we have replaced the corresponding terms of equation 10.99. I have written the same term here. So this is 10.110, the same term here. Now we know that the m squared is equal to omega k squared minus k squared. We know that m squared equals omega k squared minus k squared. You substitute for m squared here. So m squared is replaced by omega k squared minus k squared. So here. So I can write omega square k squared times this expression minus k squared times this expression. So I have written the exactly same thing. See here. So see here. Omega k squared times this expression minus k squared times this expression. So we have now 4 terms now. Look at the second term and fourth term. They are similar terms. See, almost all the expressions are similar. And this is plus sign and this is minus sign. So I have cancelled out. So second term and fourth terms get cancelled. This plus sign and minus sign. Now we'll concentrate on the first term and third term. In the third term, we have omega k squared divided by 2 omega k. So 1 omega k gets cancelled. Okay, so we have omega k divided by 2. And here we are going to use the following idea. Look at the first term. Here it is. You have this term. Okay, you have fourth term. You just look at the fourth term here. Here minus a minus k plus ak minus. Look at the first term in the third term. It is a minus k minus ak plus. Look at these two terms. So that can be simplified as AB minus BA. See here, but minus k, here it is plus k. Here it is plus k, it is minus k. So what we are going to use is, we are going to use this rule. That is summation over k equals minus 2 to plus 2. Suppose, for example, if you take 2 as k equals 2, then what is the value of the expression for your ak? Ak is nothing but a minus 2 plus a minus 1 plus a0 plus a1 plus a2. Suppose if we take a minus k, again which is equal to, this can be expanded as a2 plus a1 plus a0 plus a minus 1 plus a minus 2. Look at the right hand side, they are equal. If right hand side are equal, so left hand side must be equal. So ak can be replaced by a minus k. So using this technique, we are going to change these two terms as k as minus k. So minus k becomes plus k. So this k becomes minus k, and this minus k becomes plus k, and this ak becomes a minus k. See here. So I have simplified. I have taken this term as it is, and this third term as I have simplified using this term as k equals minus k, and I have written here. So this is equation 10.113. Now look at the underlying terms now. First, the blue underlying terms. See here, we have minus a minus k minus dagger, ak plus plus dagger. You look at this term, ak plus plus dagger, a minus k minus dagger. Look at this term, blue underlying term. It is exactly similar to ab minus ba. So we can write commutator of a comma b. And of course, commutator of a comma b, already we have seen that which is equal to 0. Similarly, look at the red underlined lines. See, red underlined terms. Again, see here, we have AB minus BA, A comma B, commutator. So commutator A comma B, again it will become 0. So the underlined terms will become 0 here. So now we have only this term, this term, this term, and this term. So we have only 4 terms. And of course, we can pull omega k by 2 common out. So we have written H equals the Hamiltonian. That is, as I discussed earlier, the modified Klein-Gordon relativistic Hamiltonian is simplified as in terms of operators, creation and annihilation operators, exactly as like this. So summation over k, omega k by 2, ak minus dagger, ak minus plus ak plus dagger plus ak minus dagger plus ak plus dagger, ak plus. See here, we just take second term and third term. Second term and third term can be simplified. We have already known this rule. That is ak plus dagger, which is equal to ak plus dagger, ak plus 1. And we are going to replace this as the first term. We are going to replace this as second one. See, second one. So this second term becomes second term plus third term. The third term becomes third term plus fourth term. See here, fourth term. Now 1 plus 1 will give us 2 here. And the first term, ak minus dagger, ak minus, we have fourth term. That can be combined together, can be written as 2 times. So 2 times ak minus dagger, ak minus. And the first term, ak plus dagger, ak plus. And the last term can be combined. We can write this as 2ak plus dagger, ak plus. I can pull 2 out and 2 gets cancelled here. See here, 2 gets cancelled. So you have summation over k, omega k, ak plus dagger, ak plus ak minus dagger, ak minus plus 1. So this is the complete expression of your modified Klein-Gordon equation. So Hamiltonian becomes exactly like this. Now the expression for your number operator for the positive charged particle is given by this, for a negatively charged particle is given by this, and this is for the particle and this is for the antiparticle for a system. So hence for a positively and negatively charged particles, we can write the energy equation exactly as it is like this. So we have H equals summation over k H bar. See here it is H bar is not there, but we have taken as H bar as 1 earlier. So we can insert now H bar omega nk plus nk minus plus 1, which is equation 10.115. So this is the complete expression for the energy of the complex field. So this one, this equation 10.115. So thereby we can get the energy eigenvalue in terms of number operators for a positively charged particle as well for the negatively charged particle. So we have quantized the energy of the photon. So this is the expression for the energy of a complex field. Similarly, one can derive for momentum total charge for the scalar complex fields. So here ak plus is nothing but annihilation operator. Ak plus dagger means a creation operator. Nk plus refers number operator for scalar particle energy, and of course H bar omega. So this is your particle energy, H bar omega. And momentum k, electric energy plus E stands for a particle, minus E stands for the antiparticle. So you have ak minus refers the annihilation operator, ak minus dagger denotes creation operator, nk minus says the number operator for a scalar particle energy H bar omega, and momentum k for electric energy is minus E, which stands for antiparticle. So to conclude, the above operators have corresponding interpretation for particles of charge momentum. We can identify that quanta with the positive charges as the particles and those with the negative charges as antiparticles. So we have particle concept and antiparticle concept. One is for n plus, another one is for n minus, nk plus and nk minus. The Hamiltonian, momentum and the total charge operators are all expressed in terms of number operators, and they are all diagonal elements. That's why we can say that they are all eigenvalues. So that is the end of this complex scalar fields, and I have derived